All right. Um, Here's going to be section 2 for today. A couple of things to go over before we hop into it. After section 1, we should have been able to draw some Lewis structures as far as some covalent molecules are concerned. So, um, if you get a chance, I'd like you to go ahead and see if you can draw the Lewis structures for each one of these three, as well as make sure you take the practice test before you leave class today. It's on Canvas. It should just be under quizzes and listed as a pre-assessment for Chapter 8. So, with that out of the way, let's hop into it. So on today's lesson, we're going to talk about rules for naming binary compounds, and basically we're going to be able to name them based on its molecular formula. Now, you think back last chapter, we had a set of rules for ionic compounds. This is going to be a similar naming scheme, but in this case, we're dealing with covalent molecules. As well as we're going to talk about how to name acidic solutions, and hopefully a couple of tricks that will help you be able to identify, okay, hey, this is an acid. Pretty light on vocab today. If you recall, we've talked about what an oxyanion is, which we know that's just an anion, a polyatomic ion with the presence of oxygen. So looking at our new one, we have an oxyacid. It's going to have a real similar definition. The only difference is we're going to classify it as an acid. So how I would say this is more or less we're going to have an oxyanion that is acidic, but we'll talk about that here in a little bit. So first off, talking about binary molecular compounds. So looking at N2O, we're going to talk about a couple of the rules here for this. So same thing as our ionic compounds, these molecular compounds here, these binary ones, we're just going to say, the entire element name. So in this case here with the nitrogen, we would just say nitrogen. And our second element, this is going to use its root, and we're going to add our suffix IDE. So again, really similar to our ionic compound rules, right? We say the first one as well as the IDE ending. So oxygen in this case, we would use oxide. Now, here's where it gets a little bit different. You recall when we were talking about ionic compounds that we just said the name and then use the IDE ending for our anion. With this one, we actually have a set of prefixes that we're going to use that are going to tell us how many of each atom are in here. So this table right here will be useful. Hopefully you understand what some of these are. So if there's one atom of something, we use the prefix mono. There's two, di. Three, tri. Four, this is where it's going to be a little bit different. Normally you would think of like quad, but we're going to use the prefix tetra. So if we have four of something, we're going to use tetra. Five, penta. Six, hexa. Hepta, octa, nona, and deca. So those are all pretty they should be pretty familiar for you, with the exception of tetra, meaning four. So looking back at this compound right here, this N2O, using these rules, we would name this. We have two nitrogens, so we'd be dinitrogen. And how many oxides? One. So the compound name here is dinitrogen monoxide. Okay, and that rule is going to follow through. Looking at this example right here, we have P2O5. So again, if we are using our rules, we should know that our first element here, this phosphorus, we're just going to name it phosphorus. Okay. And there's two of them, so we're going to have diphosphorus. And then our second one, we use the IDE ending, right? So we have an oxide, and we need to know that we have 5 of them. So we put it all together, diphosphorus pentaoxide. Now let's go and see if we have done that correctly. And you can see it is diphosphorus pentaoxide. So the naming scheme on these, it's super easy. As far as these covalent molecules go, it really is that easy. Now, there's going to be some compounds that you're going to run into that they were given common names before our naming system was developed. You know, water, ammonia, hydrazine, nitric oxide. These are all examples. So we use the name water instead of dihydrogen oxide when you use nitric oxide instead of dinitrogen oxide. And that's just because those were going to be common names that were given to these before this naming system was developed. Now, naming acids. This is where lots of people tend to get confused with some of these prefixes and suffixes that we're going to deal with. So a binary acid, all this is it's going to be an acid that contains hydrogen and one other element. So the example that we use here is hydrochloric acid, HCl, right? Binary acid, it's only made up of hydrogen and one other thing, there's 2. So when we're dealing with binary acids, so again, things like hydrochloric acid or hydroiodic acid, where we're dealing with just hydrogen and one other element, the rule that we're going to use here is we're going to use the prefix hydro, which we're using to name our hydrogen part of the compound. And then our rest of our word is just going to be, the root of the second element and then the suffix ic. So in this case, hydrochloric, and then our second word will always, always, always be acid. So HCl is going to be called hydrochloric acid. Again, this is for binary acids, meaning hydrogen and one other element. If you see more than 2 elements in there, it's not going to be this naming scheme. This next one, an oxyacid. By definition, this is going to be an acid that contains hydrogen and an oxy anion. So with this, it's not going to be binary because, looking at this example here, this nitric acid, because we have the presence of an oxy anion, which is polyatomic, which with the inclusion of that hydrogen there makes it an oxyacid. So naming rules for this, for oxyacids, first we have to identify what our oxy anion that we're dealing with. So this is where your ion chart that I've given you will be very useful, because you can see right away that we have our nitrate. Okay, NO3 minus is nitrate. We can see that. Our first word of our oxyacid's name is going to be our root. So in this case, nitrate. Okay. So it's going to consist of our root. If our prefix is per or hypo, that's also going to be included. So like if we were dealing with, perchlorate and we wanted to make it an acid, it'd be perchloric acid. But I'm jumping ahead of myself. So just know that if it has per or hypo, we're going to include that in our name. Okay. Other than that, if it has an ATE ending, we just replace it with ic. So our nitrate ion becomes nitric. This molecule right here is going to be nitric acid. The hydrogen there indicates that it's an acid, and then our naming really comes from our, nitrate ion. Okay, that's a typo there. It's not a nitrogen ion. If it was nitrogen ion, we wouldn't have the O3 minus. But nonetheless, If it ends, or if our suffix ends in ate, it changes to ic. If it's ite, so if I was dealing with HNO2, that would be nitrous acid. Okay, we would use the OUS. Okay, moving on. Here are some examples of this. So HClO3, we see our chlorate oxyanion, which means it's going to end with an IC. Our acid name for this compound is chloric acid. Next, we have HClO2. Now again, following those same rules, we've taken an oxygen away, so we have the chlorite ion, which would mean our suffix is going to be OUS. So this compound's name is chlorous acid. Okay, and then right here we have the same example that we talked about before. We have nitrate, which goes to nitric acid, and nitrite, which goes to nitrous acid. So just know the big thing here is if we're ending with an ATE ending right here, ATE ending, our acid will be an IC, so chloric acid, nitric acid. If it's an ITE ending, we have the OUS ending, so chlorous acid, nitrous acid. That's what all of these anions, when they convert to acids, this is what their names are going to be called. Okay, now a lot of these, like we talked about before, are going to have a common name, and here are some of those ones that we talked about before. Whether it's binary or an oxyacid, it can have a common name in addition to its compound name. So probably the most obvious one, H2O, we just know that as water, but if we're going to use our technical name, this is dihydrogen monoxide. 2 hydrogens, 1 oxygen, dihydrogen monoxide. Ammonia, NH3, our technical name for this would be nitrogen trihydride, right? 1 nitrogen, 3 hydrogens. Hydrazine, dinitrogen tetrahydride, because of 2 nitrogens, 4 hydrogens. Muriatic acid, or as we call it, hydrochloric acid, because the fact that it's binary and we use our H meaning hydro with the presence of that, and then we use our root word chloric acid. Aspirin. Now this one, this is going to be much easier. You see this big crazy name here, aspirin C9H8O4. You could always say 2-acetyloxy benzoic acid, but I think we're probably going to steer more towards aspirin. You went around saying that you wanted some 2-acetyloxy benzoic acid, somebody would probably look at you like you were crazy. So again, know that there are going to be common names in addition to our naming scheme that we have. Okay, now also you can probably save this flow chart. This could be useful for you. And basically what we're doing here is, if we're given a formula of something, like HBr, H2, SO3, and NO2, does the compound form an acidic solution in solution? So in aqueous solution, meaning when it's, dissolved in water. And if it's yes, which are going to be our ones that lead with those H's, we know that inclusion of our hydrogen ion is going to make our compounds acidic. So if we say yes, which our H2SO3 and our HBr are acidic, we would come over here. And then our next question that we're going to ask is, name as an acid. Is there an oxygen present in the compound? Now we have one of each here. Let's just look at HBr. This one says no. So if it's no, we use hydro as a indication of that H, and then our root, which is going to be brom, and then ic. So HBr is hydrobromic acid, which is that right there. Looking at this other one, it does have an oxyanion. It has our sulfite ion, the SO3 2-. So in this case, we're going to say yes. We have our root of our oxyanion present plus ic. So but this is not a sulfate, so it's going to be sulfite. So In this case, we go OUS because sulfite. Remember, our ITE ending means OUS. So this is just sulfurous acid. So those are our flows for naming acids. If it's not, we just use our normal naming scheme. If it doesn't have an acid, right here, NO2, we have nitrogen dioxide. Okay. So with this video, hopefully you're able to learn some of these rules to name a compound from this formula, and then as far as acidic solutions. Don't hop off yet. I have a couple of practice ones here that I'd like to go over, and when they come onto the screen, if you could pause and practice it, I'll walk through them all individually. Okay, we'll go full screen here. Okay, so with this, we have the top ones that are just going to be normal covalent molecules. We'll start here with CO2. So with this one, we know that there is one carbon. So we're just going to say carbon, two oxygens, so dioxide.
Dad, my feet are tired.
Sorry about that. Quarantined with the 4-year-old. All right, so carbon dioxide right here because one carbon, two oxygens, carbon dioxide. Next one, we have our first one, S. So that's going to give us sulfur, two oxygens, dioxide. NF3, which is going to give us nitrogen, because there's only one nitrogen, and 3F, so trifluoride. Okay, excuse my handwriting. Next, we have CCl4, so we have one carbon, so this is going to just be carbon, and 4, meaning tetra, so carbon tetrachloride. Because of the 4, that's where we use that root word tetra. Now this last one, this will be kind of challenging here. So we have As2O3. So we have two arsenics, so this is going to be di-arsenic. 3 oxygens, so trioxide. So there are some of our covalent molecules. You're going to get more practice on this in your assignment today. Now, moving on to acids. Now, first off, with our first one, HI, no, I'm not just saying hi. This is a binary acid, so if you remember our rules that we talked about, this, we're going to use the prefix hydro because of that presence of hydrogen, and then we use our root word, iodic, right? Iodic, because we're dealing with iodine, and then our second word, acid. So this acid right here is hydroiodic acid. Next one, you see this is going to be an oxyanion or an oxyacid because you should pick up right away the inclusion of that chlorate ion, okay? So here, remember, if it has an ATE ending with this chlorate, all we have to do is say this is chloric acid. Okay, next one, another oxyanion. If we separate it out, we have SO4, 2 minus. That is our sulfate. So that would make it go to an OUS ending. Okay, so all we're going to do here is sulfurous acid. Remember, OUS ending for an ITE, IC for an ATE. Then our last one, we have another binary acid because it's only 2 elements. In this case, this is hydrosulfuric acid. Now, hopefully you're able to get all those correctly. It is a little bit challenging when you first begin, but it's doable. So that's all I have. If you have questions on this, shoot me an email and I'll do my best to help. And we will see y'all on Monday, hopefully.